Hey, this is Screencast 2.3, Balancing Chemical Equations. What we're going to do is show you a combustion experiment that involves balancing the chemical equation. This is one of those where you might have to double everything at the end in order to get whole numbers. But what we also want to show you is why this really matters, why this reflects reality. And to do so, we'll show you some simple models that reveal how we're really balancing a chemical equation and what it really amounts to in the end if we could actually see these molecules, which we never seem to be able to do. Okay, so let's take a sample molecule such as butane, C4H10. There it is right there. The blacks are carbons, the white are hydrogens. It's more or less to scale, and you might be able to predict what the red-ish atoms are if we're balancing it. Each atom is oxygen. Oxygen likes to bond to itself so that we have O2 molecules. They're already drawn in their right amount, so we should end up with these numbers when we go ahead and balance this. Anytime you burn a hydrocarbon, it's going to form carbon dioxide and water. And since this is AP chemistry, you should all know how to balance this chemical equation, but let's go ahead and just do it briefly. If we started with 4 carbons, we better end up with 4 carbons. And carbon dioxide is clearly not C4O2, so we must be making more than one of them. So let's go ahead and put a 4 there. Now I don't think I'm going to do that because I know that I have to double everything at the end, but we'll need 4 of those. We have 10 hydrogens, so that amounts to 5 pairs. So we have a 4 there and a 5 there. Just try to follow this along in your head, meaning that the total number of oxygens which gets produced is 4 pairs, that's 8, and 5 singles, that's 13. Now we can balance that in terms of carbon was good, 4 carbons, but 13 oxygens in their pairs, we better write 6.5 temporarily, and that's perfect, except that none of these are unpaired. So to render that requires us to double everything, meaning that we have not 1 to 6, not 1 to 6.5 to 4 to 5, but 2 to 13 to 8 to 10. That's doubling everything. Now that little thing you just saw there is really the important part that I want to show you for this slide, which is that, is this really true? And why did we go to the trouble of coming up with these weird numbers? I guess when I click that final number there, it's going to go ahead and do the animation. But notice that when I do that, in those ratios is exactly what the rearrangement is. Only by figuring out those ratios is the only possible solution to this thing burning and forming those. Notice that not a single molecule or atom is lost, and this is the ratio they must react in it. Do we have 8 carbon dioxides? 2, 4, 6, 8, we do. Do we have 10 waters? 2, 4, 6, 8, 10, we do. Notice that we had 2 and 13 of the products. So, this balancing is an important thing since it represents what must happen in reality when these things react. So that's just a little overview of balancing chemical equations.